let me introduce. Next talk is Tauri from Remy University, and this is variation.
Okay, thank you. And also thank Becca for inviting me here. Today I will talk about Sandra's most favorite topic, variational optimization. First, let me spend some time to share my memory of Sandra. For both Sandra and me, doing physics is a rather personal experience. So I think this may explain why we get attracted to each other so naturally. I will go through several links I have with Sandra. We know each other through 2005 from this work, and also the chairman is the first author of this work. And then I was interested to check out some rather vast gauge theory arguments about RB theory. From Sandra's this work, we then think about the origin of the tunneling asymmetry in a strongly correlated background, how to understand it from the particle formalism. And then Fiji also did quite skillful work on this. And I continue to think about this issue until 2017. Then I'm confident that the conventional gauge theory argument has a serious fault. And this is published 4 years later in 2021. And my second link comes from this, my favorite paper written by Fiji and Troella. And in this work, they discovered the pi state as a best operational state for the time-lapse Heisenberg-Einstein line. It's quite important. And also, in this paper, the stochastic reconciliation method is clearly formulated. And the third important contribution of this paper is the general boson-fermion RB correspondence is proved on highly short-range triangle graph RB state. This is quite important conceptually. And I think when Sandra and Fiji is working on this program, they are not very clear about Xiaolong Wen's work on projective symmetry group. And then this is our correspondence with my correspondence with Sandra about the symmetry of this ansatz. Actually, this ansatz describes a fully symmetric symmetric state. And also this very important conceptual link between boson and fermionic RB state is one of the motivations for us to study the bosonic RB state. Commonalities, we found that actually several famous ansatz proposed previously can actually be connected continuously. For example, the Anderson's short-range RB state is in this limit, and such is the answer for the trilattice test model last year, and also the fermionic hyper state is in this way. And we have performed the bosonic RB variational calculation and found that actually this ansatz can give very, very accurate description of the ground state of this model. variational energy error is smaller than 1 solid. And then come to the third link. The third link is generated by maybe Sandro's first Chinese student, Wen Junhu. Then I was responsible for the graduate program of our department. And then, because several of our colleagues graduated from CETA, so CETA is a taking preparation of graduate students with our department. And this is the email Brony wrote to me, and we are preparing for a pre-selection exam. And yesterday I found out Wen Junhu's test paper, the copy of his test paper. So then the fourth thing, I had the chance to meet Sandro in person for the first time during our 2009 summer school. Many audience yesterday. First off, our department, many our colleagues graduated from CETA. For example, our current department head, Zhong Minlu, and former department head, Xiaoxing Wang, and also another department head is also a graduate from CETA. And in this summer school, we invited Daniel and his colleagues, and also Shui to give lecture in this summer school. And this is the title of Daniel's talk in July 21, the afternoon. I remember Daniel, before the lecture, Daniel asked me for some coffee. Hanging as proposal, but we do not have. I then asked Shihao. Shihao is a guest student of Shui. Shihao tried his best to find a bar of the next topic for Daniel. And then after the lecture, I find Daniel to visit to Great Wall. And I have a big photo of Daniel when they rested in a tea bar. But I cannot find that photo. So I tried my best to bring one. And also during the summer school, I showed Daniel my previous work. The work is done in 2007, but I kept it unpublished for many years. And actually, Sandro is the first one in the world who have a serious look at his manuscript. In this paper, we developed a variational scale to calculate the dynamical property of a strongly correlated system. And it's I'm very happy to know that in 2018, in the March meeting, Baker and Sandro both attended the March meeting. During the meeting, they told me they have applied this method to some spin model and get very accurate dynamical spectrum. So then comes to my fifth link with Sandro. In 2012, I visited CETA, and I collaborate with Sandro on the Tier-1 jetting model on square levy. So then the problem is how the model can develop a gap without breaking any tension from gaps. Previously, Sandro had very beautiful work on this. start from permanent gravity theory, and they find actually the global minimum of permanent gravity state for this model. They also get a very good rationality. So, but I think the permanent gravity state has some difficulty to describe this gas primitive in this case. So I discussed with Sandro. But then I actually first mentioned okay. I actually first mentioned that why I think Sandro's previous permanent gravity state works on this model is very important. No. Sorry. I think this is what is very important because it's done before the Xiaowang proposed his projected signature group idea. And in Sandro's 2001 paper, they found that they can get a very good rationality by breaking the symmetry of the nuclear atom. It's quite strange. It breaks the rotational symmetry in a straight way. And actually, if you look at the right panel, the right panel is I cut from Xiaowang's PhD paper. The right up panel is a spin dispersion of the state. This dispersion seems to break the quantum symmetry. But actually, this state describes a fully symmetric state. It has a very special projected symmetry class. And Sandro in his 2001 paper, actually they find this. They do not know the PhD idea. And even when Sergey and Sandro is working on the translated model, they do not have idea about the PhD. But then 1 year before Xiaowang proposed this idea, they already numerically found this useful state. So then comes the approval. So Sandro during one large Sandro told me that there's some issue about academic politics because most of Sandro's life is devoted to permanent gravity. But then I was proposing to work together on the atomic gravity. So why I think this is the permanent gravity is not enough. Because a spin matrix usually happens close to a magnetic order state. Okay. Usually occurs very close to magnetic order state. And when the magnetic order melts, the long-range spin correlation will change drastically. But the local spin correlation will be very similar to the magnetic order state. And permanent RG state have very big program to describe this local spin correlation. Because local spin correlation in the permanent RG state is already determined by the determinate type wave function. And also, these two states have very different scaling between the spin gap and the local spin correlation, local energy. Why? Why is it? Because in permanent RB state, if you want to open the gap is open on the permanent spinner. And the scaling is just like a Landau scaling. The gap, the energy will depend drastically on the gap. So when you open the gap, the local spin correlation will be drastically changed. However, in bosonic RB state, this is totally different. In bosonic RB state, if you want to open the gap, you just cut off the long-range spin correlation. Then the local energy is very insensitive to this change of long-range spin. Yeah, actually, Central clearly knows this weakness of permanent RB state. But he tried to use the problem by some trick. For example, by introducing gesture factor on some backing like wave function. I asked Central why he studied backing. He told me that this is one of the most important reasons to study this. Because the gesture factor, you can only treat the diagonal type of gesture factor. So to introduce quantum fluctuation, you have to define the magnetic order perpendicular to this axis. So you have to use the type. But Central is quite tense and quite open in mind. When I proposed my idea, actually Central helped to find this reference because when we are working on this wave function, we are not very confident about the numerical result. However, Central found this paper and told me that my numerical result stated to be very consistent with the previous bosonic RB state calculation. So we are more confident about our numerical result. And also, for bosonic RB state, the most highly part of the calculation is to calculate the permanent. And one day, Central come to my office, very excited for me that they found a way to calculate the permanent using determinant. The permanent can be calculated by pair derivative of the determinant. But when we go to the detail, we find that actually this is impossible. In principle, you can do this, but the expense, the numerical expense, is also exponential. And also, when we write the paper, Central asked me many times about the interpretation of the spin-on dispersion in the bosonic RB state. Then I'm not very sure about this interpretation. Until in 2020, I and my graduate students working on related problems, we know that for bosonic RB state, the mean field dispersion has some unphysical problem. So we should be very careful about how to interpret the bosonic spin-on dispersion. So, yeah. And this is my big connection with Central. I haven't written when I work at Central both visiting cities. And also during my visit of Britain, I think I'm indebted to both Sijing and Samuel for their encouragement on this work. Now, this work is done several years before publication. I just linked online, and both Sijing and Samuel encouraged me several times to publish it. Especially with Samuel. And this, yeah, so now I will discuss about our new development on VNC. And this work is done with my PhD student, Jianhua. Jianhua is supposed to be working with Samuel. It's COVID-19 outbreak. Yeah, the first part I just very brief. We developed the dynamical algorithm to promote to very large scale data set, combining the derivative technique and also the method. We can create a very large problem, and in this way we can study some very interesting physical problems. But now I will focus on variational optimization. And the first, I will talk about the form of the wave function, some new form of the wave function. We know that preliminary RBC has some weakness, and this weakness touches the heart of the strongly correlated system, namely how to describe the state correlation in strongly correlated parameter. This is a very tough question. So the first development is we try to use directly the RAB amplitude as a variation parameter. They are a huge number of them. But the advantage is that this variation parameter can be very easily fixed. So actually we can use such wave function without any assumption to study certain problem. Actually, we tried this on square lattice and triangle lattice. We find that actually what Samuel finds, for example, the triangle lattice near resonance the hyperactivity is already the global minimum. And also for Johannes square model, within the preliminary RV language, is already touched the global minimum. It's great. And also for the Kagome system finite cluster, is almost global minimum. And also another is we want to go beyond this this primary state by including some backload fraction. And the idea comes from also from Samuel's previous work. This study the Savant model, the backload fraction. However, for spin model, how can we go beyond this linear form? Because this backload fraction very cleverly includes exponential number of fractions into a single determinant. This is the most important advantage of backload form. But how to generalize this to the spin channel? In spin channel, the single symmetry is easily broken. So that will be very serious code. But we managed to actually solve this problem. With partial transformation, we can also devise some kind of backload. Backload not on a single particle, but on a parallel. And of course, this form still, in principle, it does not bring the single symmetry. But we have performed some calculation. We find that although the exact single symmetry is not preserved, however, given the Bachelor fraction factor is quite large, the extent of the broken symmetry is quite small. So this can be a chance to go beyond the standard RV. And another is just to use the first quantized just type wave function. Then you're not the Joshua factor, but they use the Joshua factor to correct determinant wave function. But you can also just directly use the Joshua type of wave function. For example, on square lattice hypermodel, even if you only include this term, this wave function can be extremely accurate. And also, many people may know that the Carroll signature state can be written in this form, just a form. And if you include the three-party correlation, you may include some important things. So let me go to the next part. It's about the optimization algorithm. So this is Sandra's most important conclusion. One of his most important conclusions. Stochastic transformation from limited descent to stochastic reconfiguration. You introduce this matrix, and it use this matrix to mimic the Python matrix. But this matrix only encodes the stated information, does not encode the Hamiltonian information. But in this algorithm, one problem is how to choose wisely the step length. Usually you iterate this algorithm many times, and you choose by hand the step length. One way to improve a small clip is to just use such kind of self-learning procedure. You calculate the forward direction from their inner product and choose to update the step length according to this direction. So in this way, initially you can get very big acceleration, and then the main development is to use the DFT algorithm because the stochastic reconfiguration only use the estimation only encodes the state information. Does not include the Hamiltonian information because it assumes that the Hamiltonian matrix element does not depend extensively on the ratio time. But this may not be the case. And in practice, stochastic reconfiguration, you can get stuck at a local minimum. You cannot go out. So we have tried to combine the DFT method, and this is a very brief summary of the algorithm with variational optimization. We find this combination can be very effective. When the SR gets stuck, you can still gain energy by reducing the BSPS step. And another choice is to use a conjugate gradient. Similar, but we find that actually the BSPS is as the best performance. Okay, then I spent some minutes about some application. Okay, the first one is about the U1 spin liquid with a large spin-on-firm surface on analysis. Actually, this is a very hot topic because this is, I think this may be the most physically well-motivated spin liquid. Other spin liquids, actually, we do not have so much physical intuition or why a model choose such kind of spin liquid. But for this spin liquid, there's a very clear physical argument why you should expect such kind of spin liquid. Because it can be sort of as a descendant of large firm surface metal when the charge has already gapped by multiplication, but the firm surface remains. This conjecture is supported by variational studies in paper, and in organic stock, people do find some signature of such a benefit, but there are also many versions about this benefit. And then people are using different kind of methods, for example, the variational method or the DMRG method to study the phase diagram of this problem. But there are some controversy about the two phase diagrams. And in 2021, this author also used the DMRG to study this model. Actually, this gray region is a parameter region that we should expect the US liquid, but they thought it gray, and they explained that actually there are evidence that the spin-on-firm surface state is not positive, and some other broken symmetry state is more stable. Okay. And the previous variational study does not consider such kind of possibility. And we then performed a totally unrestricted variational optimization on 12 by 12 lattice without assuming any rotational or symmetry. So with our BFCS method, actually first mentioned that this state is actually locally extremely stable. For example, if we deviate from distort this state quite a large bit, and then operate the optimization, we still find the system will go back to the state. However, this is only a local state. It's not a global state. With BFCS, we find that actually we can go out. And the energy gain is huge. This F state, the energy, for example, the 12 by 12, and rate change is 15%, is this value. But if we fortunately go up this local minimum, you'll find that actually the original energy can be significantly lower than this one. Then what's this new shadow point? We plot the spin correlation. We find such kind of a very strange pattern, and we try to figure out what kind of structure is encoded in this state. And we find that actually it has as 4 by 6. Okay. Yeah, I have a 4 by 6 periodicity in spin correlation. And we then map out the phase diagram variationally. We find that actually there are three phases. For small rate change, the system stays in the high class phase. And for larger rate change, it's 4/6 periodicity state. And there's the intermediate phase. The intermediate phase has a different periodicity. And this phase diagram has strong similarity with exact diagonalization phase diagram on 6x6 cluster. If you zoom in this part, you find here you also have a level cross. So you have a intermediate phase. Okay, so this summarizes. This is from surface state here, and the two continuously state here, and this is the pipeline. Okay, let me go through this quickly. The second application is we consider when the fluctuation makes disorder, what will happen? Because the disorder can release local fluctuation, and this effect can act as an avalanche-like way, and to affect further remove structure. And also, the RV structure is actually an emergent structure. So this RV structure, the emergence of this structure depends delicately on the balance between different plastic properties. So when you introduce impurities, you break this balance. So this emergence of this RV structure is bound to be very vulnerable. And this is to be supported by recent experiment findings. For example, they found that very tiny amount of impurity can induce very large inhomogeneity in the training population. For example, NMR measurement found that for worldwide system, tiny amount of impurity can induce about 60% of inhomogeneity in the carbon tank. So this is we then from variational study of the carbon we introduced a pair of distinct impurities in the carbon tank and perform variational optimization to see what will happen on the RV parameter and what will happen on the local susceptibility. So this shows when you increase the magnetization, this is the lowest magnetization. When you increase the total magnetization, you find that this magnetization will have very ununiform distribution on the lattice. So if you measure the local susceptibility, you will find a very strong fluctuation. Only 2 impurities on 432 samples. And the last one is we try to solve one mystery of hydroxyfluoride. Namely, in the overload region, you find that the root weight actually increased with whole concentration. However, the superfluidity goes down. This is a very unnatural from the feedback picture. So some people think this may be a disorder, but actually one author argued strongly against this disorder picture. They gave 10 main reasons why we our motivation is that actually here RV parameter is also a emergent parameter. So impurity can have a very strong effect on this RV structure. And so the same impurity, zinc impurity, doped into different background. For example, if you dope zinc into a well-ignorant background, it may not have strong effect. But if you dope into a strong correlated background, for example, in the teacher model, you can have very strong effect. So this is our motivation, and then we perform variational optimization for the teacher model with a single impurity. Let's see what happens. So this potential here with very strong peak, and polar condensation also here has a very strong effect. We know that zinc impurity will supply rapidly the superconductivity in the fluid. So let's see how this can be achieved. This three figures shows how the RV parameter is affected by a single zinc impurity in zinc. And then we calculate the superfluid density by inserting a flux and calculate the variational energy as a function of this flux. From this figure, this is a 12% doping. If you do not have zinc, you'll find that actually this is the diamagnetic response. You'll have a large probe, a large superfluid density. And if you introduce zinc, but do not consider paramagnetic response, you get this one. It's reduced a little bit. But if you include impurity and also consider the paramagnetic response, you'll find that superfluid density will be significantly reduced. And this is my last page. So when you have calculated the doping independence of this superfluid density, in surface, the superfluid density depends on the whole concentration non-monotonically. First the rate and then decrease. But if you do not include the impurity, you'll find that actually the superfluid density will increase monotonically. But with the inclusion of the impurity, you'll find that first the magnitude of the superfluid density is slightly reduced. And then the doping dependence becomes non-monotonic. Okay, so I finished on my comments, and thank you.
This optimization method, this optimization is a parameter? The optimization method.
Yeah. You can use a given step length, but also you can perform linear search. Within the linear search, you have two revisions. Along the searching direction, you revisit your variational energy.
So what do you mean by this? Improving the optimization process in this case? My understanding is that the standard stochastic reconfiguration mimics the Hessian matrix by some converged matrix of the state vector. And this matrix encodes the state information, how the state depends on the variational energy. But actually, when we calculate the variational energy, the Hamiltonian matrix element also contribute. So the two Hansen matrix has contributions from both the phase vector, the wave function, and also the matrix element. So this can be important. The matrix local energy depends on the ratio of the wave function. So this can be important.
So maybe that's exactly you do a strong statement that you do a strong statement that a U1 spin liquid is unstable to disorder in the RG sense. Is that is there?
I think in the variational sense, we find that actually you can have a much lower energy state.
So it is so also in the RG, if you do an RG calculation, you would say it is relevant all the time.
Yeah.
So if you that would be an question to so if maybe for Andrew, if you put this order at a DQCP, then this would go is that if you put this order at DQCP, that would is relevant.
Yes, we have studied that, and definitely you get a very different, destroy the critical point, and you get a different test.
Okay. Any questions?
Yeah, I actually have a technical question. So, if you do a fixed load calculation after this variational calculation, will the state change after that?
Yeah, fixed node we do not have the technique. We do not have the code to perform fixed node technique. Yeah, so maybe you can.
No. I don't.